So one of the last things that I want to show you in this video is an example of a more useful 2-qubit quantum circuit. This is a circuit that creates a Bell pair, an EPR pair. So we wish to create this state here, starting from 2 qubits that are initialized in the state ket0. So before showing you this circuit, I want to pose it to you as a challenge to come up with such a 2-qubit quantum circuit, which starts from ket00 and ends up with an EPR pair. Now, as usual, you should feel free to pause the video and think about it, as it might take a little bit of time to come up with the circuit. So here is the promised 2-qubit circuit. It first applies a Hadamard gate on the first qubit, and then it applies a CNOT gate from the first qubit to the second. So if we were to draw it, this is what it would look like. Now let's analyze this circuit together and verify that indeed it maps 0,0 to an EPR pair. So we start off with the state ket00. Now we're applying first the Hadamard gate on the first qubit. So the state of the second qubit stays unchanged. It remains ket0, while the first qubit is mapped to 1 over square root of 2, ket0 plus ket1. Now we can expand out what we got and realize that this is equal to 1 over square root of 2 ket00 plus 1 over square root of 2 ket10. So we're almost there. We're almost at the EPR pair. What we would want is 00 plus 11 instead of 00 plus 10. So we're almost there. And now what we do is we're applying the CNOT gate. And this, recall that it flips the second qubit if the state of the first qubit is 1, and it does nothing otherwise. So when we apply a CNOT gate, now remember that it acts by linearity. So a CNOT gate on the state 00 does nothing because the first qubit is in the state 0. But applying a CNOT gate to ket10 maps it to ket11. And so we obtain, all in all, exactly the EPR pair that we desired. And you can take a moment to digest this calculation before moving forward. So I want to leave you one last exercise, which is the following. So we created a Bell pair by using a Hadamard gate and a CNOT gate. Now a similar state, but for a 3-qubit system, is called the G at Z state. And it is the following. It's 1 over square root of 2, 0, 0, 0, plus 1 over square root of 2, 1, 1, 1. So using only Hadamard and CNOT gates, the exercise asks you to construct a circuit that creates the G at Z state. Now I won't solve this here, so this is homework for you to do on your own.